This video is based on to help students with working on chemistry, specifically topics of electron and light and atomic structure. If you're learning it from my course materials, this is the 7th assignment that I usually give students with like an atoms first approach to chemistry. So let's just go ahead. I'm going to go through a few problems, just whether you're following along for the first time you're seeing these or if you've already just using this as an answer. All right, so just as a quick review, this is the kind of the problem-solving strategy and the equations that we'll be using in this video. Again, if you're interested in the more the understanding of where the speed of light's coming from and Planck's constant, all that kinds of stuff, watch the other videos that have background information on that or the slides. This is more just of a problem-solving video to see if you can interpret the information and apply it to these equations in order to get the answers, and also how to express that in scientific notation and significant figures as well. All right, so this first problem is ultraviolet radiation has a frequency of 6.8 times 10 to the 15th 1/seconds. So 1/seconds, we also sometimes call that hertz. That is the unit that we use for frequency problems or for the represent frequency. So calculate the energy in joules of the photon. And joules is the primary unit we use for energy. So we see that we kind of want to problem solve. We see that they're asking for energy. So we're probably going to be wanting to solve for E based on the equations that we have in this section. We know that we're probably going to be using something like this because that's the only one we have that involves E. And also we see this is a frequency, and that little V symbol there, that is for frequency. That's not for velocity, it's for frequency. I think it's based on a Greek letter that looks similar to V. So since we know this, and actually we know this too, this is Planck's constant. So this is defined as basically like the smallest amount of anything. I think that's a bad way to say it, but I think that's essentially what it is. And this is times 10 to the negative 34th. And we know the frequency right up here, it was 6.8 times 10 to the 15th 1/seconds. Oh my gosh. So that's essentially it. We just have to multiply those together. So we want to pull out our calculator and go ahead and do that. So I'm going to calculate right along with you. So we would want to, in our calculator, multiply the two values. Again, we do have a discrepancy in the number of significant figures, so we're not going to worry about that till after the calculation, though. For those of you guys who've been doing some chemistry a while and follow along about how to do these in the calculator, I would highly recommend you write it in like this, 6.85 e to the 15th. That's going to save you a lot of time and little errors where maybe you have a parentheses here or there. So go ahead and do that. I'll calculate this answer. Can probably have beat me to the punch at this point. Divided by 6.26 to the negative 34th. All right, and I get my gigantic answer. Oops, did I divide? I should have multiplied. Oops. Okay. All right, so my answer here, when I multiplied these two values, 6.26 times 10 to the negative 34th, and I 4.50568 times 10 to the negative 18th. And I actually even have my calculator in the setting that it even writes it in that notation. So I'm just like always operating in scientific notation. And that's pretty much it, folks. That's how we have it. Wait, we have to round to the right number of significant figures. So we're going to put 4.5 since the original value, then the least specific measurement we had was 2 significant figures. We don't even worry about this 4 because it is a constant. It's an exact number. We don't have to worry about that. So it's going to be 4.5 times 10 to the negative 18th. And then our unit is joules. Joules is a compound unit made up from there's some kilograms in there, and there's some meters squared, and there's some seconds squared on the bottom, but it all cancels out, and that's what we should have got for our first answer. Okay, so let's move on to the second one. Find the energy in joules per photon of microwave radiation with a frequency of 7.91 times 10 to the 10th hertz. So exact same thing. We're looking at E equals the Planck's constant times the frequency, and this time we're given the frequency again. So it's another pretty straightforward problem. 626 times 10 to the negative 34th, and then we're going to multiply times the frequency of the microwave radiation that was provided, which was times 10 to the 10th. So even if we don't usually do a lot of math in our heads, and most people don't like to do that, but you can kind of make a prediction about the magnitude of the answer if you just remember your exponent multiplying rules from math class. So since we have a negative 10 to the negative 34th times 10 to the positive 10th, I bet the answer is going to be somewhere in the magnitude of 10 to the negative 24th, because when I multiply exponents the same base, I add them together. All right, so the answer I got was, and if I make a mistake, feel free to correct me in the comments. I am human too. I'm a little bit of a clumsy human, by the way. So we see that this has 3 significant figures. Actually, that's our only data piece. We don't look at this. This is just talking about the magnitude. We don't look at the Planck's constant as significant figures because it's an exact value. So we're going to round our answer to 3 significant figures. So we'll have 5.4 times 10 to the negative 23rd joules. All right. So next one. All right, a sodium vapor lamp emits light photons with a wavelength of 5.89 times 10 to the negative 7th meters. What is the energy of these photons? All right, so here's a problem talking about sodium lamp vapors. If you have done the flame test lab in class, you probably know that sodium is yellow. And hey, if you know a lot about color, you might know that's not yellow. But 589 nanometers is usually about a yellow color, maybe a little bit of like an orange yellow. Okay, so this time we were told a wavelength and we want to know the energy. So, we have this. This is the only equation I remember with energy. So sometimes you're like, oh my gosh, what do? I don't have a wavelength. Well, think about it. Whenever an equation I want to use and I don't have the right data to work with it, do I have another equation that can kind of be like a bridge between the two? And we do. And that is the equation. Let's go back so you can see what I'm talking about right here. You can write it this way, or you can write it this way. Essentially, the speed of light equals lambda times the wavelength. Hey, we got a number here and here. So that tells me that if I have the same variable in 2 equations, I can probably relate it and kind of substitute it in. So I'm going to do a little bit of quick algebra and solve for frequency by dividing both sides by wavelength. And now I have an equation for speed of light over wavelength. So that's how I want to solve it. So right here with that, I'm going to plug it in here. And now all of a sudden I have a new equation. Energy equals Planck's constant times the speed of light, which is also constant, all over the wavelength. These two numbers I know, they're given to me. I can look them up, or actually I should probably memorize them because I'm doing so many of these problems. So 6.626 times 10 to the negative 34th. And then C is going to be 3.0 times 10 to the 8th. Your teacher may have you use a different level of specificity there. So you might be using 2.99 or something like that. That's cool. Just follow what you're supposed to do. And then since we do want the answer in joules, we are going to be using meters as our units. Technically the units that a joule is made up of, and here's how I always remember it. Energy equals 1/2 mv squared, or maybe you remember energy equals mass times acceleration of gravity times height. So I know that there's going to be at least a kilogram in there. There's going to be some meters. There's going to be actually 2 meters squared, and there's going to be a second squared as well. So those are the units I'm looking for and then so I want to keep everything in those. I have to convert if I'm given grams or nanometers or something like that. So this is going to be times 10 to the negative 7th meters. And that's pretty much it. So I'm going to go ahead and type this in my calculator and see how many joules I get. You're going to notice that a joule is actually like, it's not a lot of energy, but if we're talking about like single electrons and stuff, it's a lot of energy. So you're going to see a lot of very small, like fractional joules. Sometimes when they're talking about energy and they're talking about electrons, you might actually hear electron volts, but the standard unit, the SI accepted unit, is going to be joules. So I usually will multiply all the numbers in my equation first and then divide by all the numbers on the bottom. Okay, and this is at least what I got. It's going to go on really long, so I'm already going to check. I only need 3 significant figures. It's going to be 3.37 times 10 to the negative 19th joules. So a single photon has that much energy. Now, there's obviously going to be a ton of photons coming out of that lamp, so it might be a little bit more in reality. All right, last one for this part 1 of the video is one of the electron transitions in a hydrogen atom produces infrared light with a wavelength of 7.646 times 10 to the negative 6. What amount of energy causes this transition? Okay, exact same setup. I'm going to write the other equation as well. All right, and usually your teacher might provide this on an equation sheet, or you might have to memorize it. It matters how it is. Some students just memorize this. I tend not to memorize these compound equations, although they might seem like a shortcut. I feel like it's easier just if you remember the base ones, you can kind of derive the ones you need on the fly, especially if you're good at algebra. If you kind of struggle with algebra, then maybe you want to memorize this like separately. I don't always think memorizing is the best strategy, though. All right, so energy equals 6.626 times 10 to the negative 34th times 3.0 times 10 to the 8th all over 7.464 times 10 to the negative 6. And that's what we're plugging in the calculator real quick. So luckily I already had that top part saved. And let's go ahead and do this part, 7.464. I think you're supposed to do the calculations before you make the video. Uh-oh, especially when you have typos. Okay. Dun, 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 moment of truth. Okay, I'm looking at the energy here is 2.66 times 10 to the negative 20 joules. All right, so hope that helped you with those first couple questions. Part 2 of the video is going to have a little bit more about finding other variables as well. So happy studying, and come back if you want more help in chemistry. Like and subscribe. Bye.